Okay, so title shows it is a basic course in real analysis, and the topics which I will cover in this course are date kinds theory, okay. So, the topic which I will cover first is the date kind theory of irrational numbers. The second topic which will give the Cantor's theory of irrational numbers. Third topic is our sets, which will include all bounded set and the open, closed and compact, etc. Then continuity of the function, of course, real valued functions we will take, then differentiability, then we will go for the Riemann integration, as well as also we will go for the Riemann Still J's integral. Then we will go for, after this, if the time permits, then we will go for the improper integrals. Though it is not listed in the part, but if the time permits, we will give an idea of the improper integrals, both type, whether the upper limits or lower limit is infinite, minus infinity to infinity or 0 to infinity, or the case where the limits are finite, proper integral, but the function is discontinuous at some point in between, say minus 1 to 1 by x dx. Then x at the point 0, the function is a discontinuous function. So, though the limit is finite, but the function is discontinuous, it will be treated as a improper integral of the second kind, and the sum integral like 0 to infinity and some function f x dx or minus infinity to infinity f x dx, that is also considered to be, and in particular cases our beta gamma functions, which are very useful for those in engineering branch. Okay. So, these we will cover later on. Now, the first two chapters which we will discuss, the date kind theory of irrational number and Cantor's theory of irrational number, is basically in what manner the real numbers has been developed. Actually, we know the set of sequences, we know the natural numbers starting from 1 to 3 and so on. Then when we add two natural number, we get a natural number, but when we subtract the two natural number, then we also get some number which is 0 or sometimes negative also. So, an idea of the generating the whole numbers comes in picture, that is when the natural number is supplemented with 0, 0, 1 to 3, this is called the set of whole numbers. And similarly, when the negative integers is also included, all the 0 positive integers, negative integers as well as 0, then this is called the integers. And then idea when we apply the addition, subtraction, then any two integers when we add, we get always integer, when we subtract two integer, we always get integer, but when we divide the two integers and the denominator is not 0, then we not necessary to always get an integer. So, that gives an idea of the further extension of the number system, and that leads to the concept of the rational number. And since always the numbers may not be of rational, that is a number which is square root 2 or such, this we will prove is not a natural, is not a rational number. So, again the idea of enlarging this set of rational numbers again leads to the concept of irrational number, and then rational together with rational will lead to the real number system. But how this development has been done, that is given by the date kinds in one in terms of the sections and cantors also in terms of that. Okay. So, we will give an idea of the development of this number system in these two chapters, and later on we will go over each one. Okay. So, that is the idea of it. The books which I will follow is the routine book, Water routine. This is the principles of mathematical analysis, principles of mathematical analysis. This is a Tata McGraw-Hill book, it is available. Then second book which I will follow is Sterling K. Barbarian, a first course in real analysis. In real analysis. Then we will also follow the book M.H. Porter and C.B. Morey. This is a first course in real analysis, same title, a first course in real analysis, and this is basically a Springer-Verlag book. Springer-Verlag, this is also an Springer-Verlag book, and this is McGraw-Hill. Okay. So, these are the books which we follow, and in Indian authors you can go a Santinaran book, or maybe there is one book that is by Sharan, N. Sharan, that also a good book, that is a theory of function of real variable, theory of functions of real variables, Okay. So, that is these books is more than sufficient, or you can go to any other book. There are so many books are available on real analysis where you can. Okay. The first one. So, this is what. Now, let us see the first Dedekinds theory of the rational numbers. So, we will start with the say rational cuts first. We know the rational numbers. Rational numbers, a number of the form, p by q, where p and q both are integer. Q is not equal to 0, and normally we take q to be a positive, q greater than 0, and also assume there no common factor, p and q have no common factor, p and q have no common factor. So, a number of the form p by q, where p q both are integers, q is not equal to 0, and normally we take q to be greater than 0 and start allow p to vary over the integers. Then we get all sort of the number which are called the rational numbers. And these rational numbers, if we have the two rational number, then addition, subtraction, division, multiplication. Division means when q term is not equal to 0, when one term is not equal to denominator is different from 0. Okay. Then division is possible. So, if we apply the operation of addition, that is if two rational number if I add, you get again a rational number. If I subtract the two rational number, again we get a rational number. If I divide the two rational number, provided the denominator is non-zero, then also we get a rational number, and when we multiply the two rational number, we also get a rational number. So, basically it satisfies all the algebraic operations which are available, addition, subtraction, etc. And not only this, this set of rational number is an ordered field. This set of rational numbers is an ordered field. Ordered field, we mean that if we pick up any two rational number from the collection of the rational point numbers, then one can easily identify which number is greater than the other, or which number is lower, less than the other, all they are equal. One can easily identify the relation between the two number which is less than, greater than, or equal to. So, any two number alpha 1 and alpha 2, these are two rational number. Q is the set of rational numbers. Then one can easily identify whether alpha 1 is less than alpha 2, or alpha 1 is greater than alpha 2, or alpha 1 equal to alpha 2. One can easily identify. And not only this, if there are three numbers, then suppose alpha 1, alpha 2, alpha 3, these are three rational numbers, and if alpha 1 is less than alpha 2, alpha 2 is less than alpha 3, then easily one can show alpha 1 is less than alpha 3. That is the associative property in case of this. That is alpha 1 is less than alpha 2, alpha 2 is less than alpha 3, then we get the transitive property, is it not? Then alpha 1 and alpha 3 is also related with the less than sign. So, this is what we have. A very interesting property of this rational number is that between any two rational numbers, say alpha and beta, there will always exist a rational number lying in between alpha and beta. That is, if alpha is this number, beta is this number, one can always get a rational number which is say alpha plus beta by 2 lies between alpha and beta, that alpha is less than this, which is less than beta. Okay. So, we can always find out the number in between alpha and beta, and this is true for any, this is also a rational number. So, in fact, between any two rational number, one can introduce infinite number of the rational points in between two. So, basically that is between any two rational number numbers, one can introduce infinite number of rational points. Is it okay? Clear? Now, suppose I represent these rational numbers by means of a point on a straight line, by choosing say fix a position of 0 and then fix the length of the identity 1, and then on this scale one can find out a location of a rational points on these real lines, on this real line, is it not? Depending on the length, how much distance is from the 0, say 2 by 3, it means its distance from the origin is 2/3. So, you can have this point like 2 by 3, say minus 2 by 3 and so on like this. So, the rational point can be arranged or can be located on the identified by a point on the real on a line, straight line. Now, will it complete the entire real line? Will it absorb all the points of the real line? Or in other words, what I mean is that can you say, because between two rational number we can always get an infinite number of rational points. So, and if I arrange this rational point on the some straight line, then can you say the entire straight line minus infinity to infinity is filled up by means of rational point? The answer is no. That is, there are the points lying on this straight line which are not at all rational point, not at all rational point. So, those points which are not at all rational point, we cannot be put it in the set of rational number. So, it means the set of rational number is not at all complete, is it not? So, we need the further extension of the rational point. Now, for example, if we take a point under root 2, square root of 2, okay, we claim that square root of 2 is not a rational number. Is not a rational number. This is our claim. Suppose I prove it by contradiction. Suppose it is a rational number, then it must lead to a contradiction. So, suppose it is not true. That is, the meaning of this is, that is, under root 2 can be represented by means of p by q by a rational point, where p and q are integers, q is greater than 0, not equal to 0, and p and q are not having any factor common, any common factor. Are not having any common factor. Is it okay? Suppose I prove it by condition. Suppose I assume the root 2 is a rational point. It means root 2 can be expressed in the form of p by q, where p and q both are integers, q is not equal to 0, q is positive, and p and q is not having any factor common. Is it not? So, that is, let us see. So, we get basically now. So, what we get is that p by q is equal to root 2, clear? Square it. So, this implies p square is equal to 2 times of q square. Okay. Now, p square is 2 times of q square. It means what? That p square is divisible by 2, because q is integer. Q is integer. So, q square will also be an integer. So, if I take p square by 2, you are basically getting an integer. So, what can you say? This shows that p square is divisible by 2. Is it clear? Now, if p square is divisible by 2, can you say the p is also divisible by 2? If p square is divisible by 2, then p, can you say it is divisible by 2? Divisible by 2, because the reason is, if it is not divisible by 2, suppose p is not divisible by 2, it means what? The p by 2 is not a integer, is not an integer. So, if it is not an integer, when you square it, what will happen? The square of this will not be an integer. So, you are not getting the q square. You follow me? You are not getting an integer. So, again guys, so if p square is divisible by 2, the p has to be divisible by 2. Okay. It means, when p is divisible by 2, then p can be written in the form of 2 times r, where r is some integer. Is this clear or not? Okay. Or I will explain again, like suppose when we say p square is equal to 2 q square, will it not imply p square is an even integer? Even integer what? The integer which are multiple of 2, these are the even integer. So, p square is an even integer. So, square root of this p, if p even integer means it is divisible by 2. So, square root of p will also be an even, because if p is not even, the square of this may not be even, because say p is 3, what is the square? Is 9, it is not an even integer. So, if p square is even, the division of this square root of this will be even number. So, that is why we say p is also divisible by 2. Okay. Once p is divisible by 2, p can be expressed in the form of 2 r, where r is some integer, then only you can divide by 2, you are getting integer, otherwise not. So, substitute it here. So, what we get from equation 1? So, from 1, if I substitute, then what you get? Q square becomes 2 times of r square. Is it clear? Again the same argument, it means what? Q square is divisible by 2, is divisible by 2. So, q must also be divisible by 2. Q is also divisible by 2. It means p is also divisible by 2, this is 2, q is also divisible by 2, it is 3 equation. So, what do you get? A common factor 2. So, 2 and 3 implies that p and q have common factor 2, that is 2, which leads a contradiction, because if root 2 is a rational number and expressed in the form of p by q, then p and q should not have any common factor. So, a contradiction is reached, and this contradiction is because of our wrong assumption that root 2 is a rational number. It means this implies root 2 is not a rational point, is not a rational number. Is this clear? Okay. And in fact, this is the one example I have taken. You take any square root of a positive integer, any square root, square root of any positive number, say under root 5, under root 6, under root 7, this all will be a irrational numbers. We call it this later on as a irrational points, which are not rational. Okay. So, it means the set of line, the set of points, rational point on the line is not complete. There are all gaps, which gaps can be filled up by means of these irrational points. Okay. How to introduce this irrational point? That is done by the Dedekind. Okay. How did he introduce this rational point, concept of the irrational point? That is done by Dedekind, and same in the Cantor's. Okay. Now, let us look another thing from root 2. If we say root 2, and suppose I just calculate it square root of 2 by using our calculator, then what value you are getting? Suppose first 1, then 1.4, only first decimal place, then 1.41 second decimal place, and if I continue this, then what you get? 1.414, then 1.4142 and so on. Just take the square root using your calculator with the first decimal place, second decimal place and third, and continue, is it not? Now, if I square these, so square of 1 is 1, square of 1.4 is nothing but 1.96, square of 1.41 is coming to be 1.9881, then 1.999396 and so on. This is square, is it not? Now, if I plot this point, what is it? this sequence of the squares, does it not tending to 2 from the left hand side? This is our 2. You are getting the points which are approaching towards 2, is it not? So, and these are all rational points, because you can write this 1 by 96, 1.96 is 196 by 10 square. This you can write this divided by 10 to the power 4 and like this. So, these are all rational points. So, a sequence of the rational number is obtained from the left hand side, which is approximating 2. Is it clear? Now, if I add one digit in each term, or increase one digit in say this is say alpha, I take in alpha. So, what we get here, you are getting 2, one digit more 2, here you are getting 1.5, here you are getting 1.42, 1.415, 1.4143, just increase the last digit by 1, increase the last digit by 1, one digit, increase last digit by 1. Okay. So, you are getting, now if I square again, what you get 4, this is something like 2.25, this is something 2.0164, 2.002225 and so on. This is 2.00024449. So, what you get now? You are getting a sequence of these points. This is 2. You are getting a sequence of the rational number which are approaching to 2 from the right hand side. So, 2 is sandwiches. You are getting a sequence of rational number which is approximating 2 from the left. You are also getting a sequence of rational number which is approximating 2 from the right hand side, and the limiting point is coming to be the root of 2. The sequences are rational, but limit point is not a rational point. Is it clear? So, that gives the idea of the irrational number. It means the irrational numbers, they are basically a number which can be approximated by means of the rational points, okay, by which can be approximated by means of a rational points, and it lies always in between 2. Any 2 rational number is there, we can always get a rational number as well as irrational numbers in between 2. Okay. So, that is this clear? Any doubt, please? Okay. Now, one more thing is, for we can divide the whole rational number into 2 classes. Suppose I say the set of all rational number whose square is less than 2, and the set of those rational number whose square is greater than 2. If I say that class set of, suppose I say one can, or we can divide the positive rational number numbers into 2 classes. 2 classes, one containing the number 1, containing the numbers whose squares are less than 2, and the other one contain the other, and the other whose square, okay, and the other those whose squares whose squares are greater than 2. Greater than 2. So, this is our 2. Okay. We are taking those rational number whose square is less than 2. Okay. Then that class we will denote by L. Okay. The first class, this one containing the number whose square are less than 2, this will be denoted by L, and the those rational number whose squares are greater than 2 we denote by R. So, all the rational number will be either in L or will be in R. Any rational number you pick up whose square is greater than 2, you write in R. If it is in this, you write in R, L. So, this way we can entire rational number we can separate out in the form of these two classes, one L lower class and one is the upper class. And then what about the 2? 2 does not neither belongs to L nor belongs to R, is it not? Because it is not at all the rational point. But suppose I take the set of those rational points which are less than equal to 1 and those which are greater than 1. So, all rational number which are less than equal to 1, it will include all the points less than equal to 1, all the points which are lying towards the left of 1 and the point which are strictly greater than 1 lies toward the right of the 1, and 1 itself is a point in lower class, because lower class I am choosing those rational points which are less than or equal to 1. Clear? So, and 1 is a rational number. So, it means the entire real line we can entire this number system we can break up into the classes lower class and upper class, and these classes are also of two types, where the point which breaks up the two classes, the point lies in the one of the class or may not lie in the one class. The point which lies in the one of the class will correspond to the rational number. Okay? Like say 1 lies in there. So, the entire class we say it corresponds to 1, but the point which does not lie in there, that correspond to the irrational number. So, like under 2. Okay. So, that will give the classification. Is it correct? Now, these classes have certain property. The properties these classes have some properties. The first property is that every number of R, R means upper class, remember this we call it as a upper class. Every member of R, every member of R is greater than every member of L. Which is obviously true. The second property says that there is a number of L means lower class, and a member there is a number of L or there is a member of L. Why I am writing number? There is a member of L and a member of R whose difference is as small as we please. What do you mean by this? Suppose this is our lower class, this is a upper class. Okay. What it says is there is a member of the lower class, say suppose A is a member of the lower class and a member of the upper class say B, such that whose difference is as small as we please. This we wanted. Okay. Then, so, let us say let A belongs to the lower class, B belongs to the upper class. So, B minus A will be positive. Let A belongs to the lower class, B belongs to the upper class. Why A minus B minus A greater than 0? Because the elements of the upper class will always be greater than the elements of the lower class. So, B minus A greater than 0. Is it okay? Now, this length B minus given any epsilon, given epsilon greater than 0, one can find n. One can find n such that B minus A by n is less than epsilon, because B minus A is positive and epsilon is suppose 10 to the power minus 2. So, you can choose n such a way, so that the B minus A by n is less than 10 to the power minus 2. Let it be d. Okay. So, what we get? You are starting with A, next term will be A plus d, then A plus 2 d and so on, A plus r d, A plus r plus 1 d and like this, and last term is A plus n d, that is equal to B. Is it okay? These are the classes. Is it correct? Like this. So, we are getting this thing, A plus n d is B and A is the. Now, A is in the lower class, this is our A is this side, B is this side. You are introducing the point in between A and B by this. This is A, this is the new point, this is another point, this is another point like this. So, as soon as you introduce the point, there will be a cross, this will the point will cross this line, is it not? This which line that divides between lower and upper class. So, this is the line, here is L, here is R, this is L, this is R. So, a R will come, a number R will obtained. So, that A plus R d belongs to the lower class, while A plus R plus 1 d belongs to the upper class for some R, is it not? For some R, for some R, this will happen, because you are continuously dividing and then approaching A. So, when you go slowly here, a point will here, some point will be here and immediately it will jump, it will go to this. So, for certain R, this point is A plus R d, this point is A plus R plus 1 d. Okay. Now, what is the difference of this? So, difference of this will be of these points is nothing but what? Is nothing but d. You see this minus, and d is always be less than epsilon. So, what our claim is that there is a member of IL and that member is A plus R d, and a member of R, that is A plus R plus 1 d, whose difference is can be made as small as we please. Epsilon is a given choice. So, you can choose any epsilon, accordingly you can identify the 2 points whose difference can be made less than epsilon. Clear? So, this is the second property which okay. Third property says the class L, has no greatest number and the class R no least number. In case of square root, remember when the class is produced by square root, I am not saying rational point. No. In case of the square root, which is set of all rational number whose square is less than 2, is a lower class, set of all number whose square is greater than 2, for that class lower and upper class, lower will not have any greatest number, upper class will not have any, that is the class L, lower class L, which contains all rational numbers whose square is strictly less than 2, and the class R which contains all rational numbers whose square is greater than 2. Okay. Now, these classes, for these classes property third hold. That is, in this case, the lower class will not have a largest number and upper class will not have a least number. Suppose I have, for example, proof is, okay. Suppose A be a, suppose A belongs to the lower class, that is, the A square is less than 2, is it not? So, 2 minus A square will be positive. Okay. Once it is positive, you can identify the number A 1. So, there exists a number A 1 belongs to L, there exists a number A 1 such that 2 minus A 1 square, which is less than 2 minus A square, is it not? Because there is a gap, 2 minus A square is greater than 0. So, basically this is our 0, here is somewhere thing number 2 minus A square. So, again there is a gap, in between we can identify some rational numbers, is it not? Which like, so you can find a 1 such that 2 minus A 1 square is less than this, but what do you mean by this? This shows A 1 is greater than A. 2 to get cancelled, minus A 1 square is less than. So, when you multiply by minus, order reverses. So, it is greater than A. It means, if I claim A is the largest number, which is not true, because you are able to get another number A 1 which lies in L, which is greater than A. So, L cannot have a largest number. Okay. Similarly, one can show for the upper class R. Similarly, so L cannot have largest number. Okay. Cannot have a largest number. Similarly, R cannot have least number. Is this okay? Now, based on this our discussion, we can now introduce the concept of cuts of rational points. Okay. So, that is also called the sections. So, based on this, now we introduced the sections of rational numbers. Sections of rational numbers. Okay. So, what we say is section of a rational number, sections of a rational number, section or cut of a rational number, section of a rational number can be constructed with reference to any two property. Any two properties, say P and Q, which are mutually exclusive, and one of which is essentially and which are mutually exclusive and one of which is essentially possessed by every rational number. By every rational number. Let us see what is the meaning of this. When we say the section of a rational number can be constructed with the reference to any two properties, say P and Q, which are mutually exclusive and one of which is essentially possessed by every rational number. Say for example, when we say the set of those rational numbers, set of rational numbers x which are less than 1, okay, and the set of rational numbers x which are less than 1 and set of which are not less than 1. Suppose I give these two statement. Set of those rational number which are less than 1, I denote say L, this is R. It means what? L is the set of those rational number Q such that x is strictly less than 1. So, what is the property? Property P is less than. So, here the property P is less than 1. This is the property which you are imposing, is it not? Set of those rational number, set of those point x such that x is less than 1. So, x satisfies this property. And what is R? R is the set of those rational point such that x is not less than 1. It means what? It will be greater than or equal to 1. That is, here Q is not less than 1. So, this is the property. So, what he said that every rational number can be constructed with reference to two properties P and Q. This is the property P, this is the Q. Clear? So, the 1 is the number which can be separated out or which can separate the rational number into two classes. One is the L class, other one is the R class, and R contains 1. R contains 1. Clear? So, this R which is in upper class and L is the lower class, and this is represented by 1. If I say the section L R is represented by 1, then what do you mean by this? It means the L lower class contains those rational number which are less than 1 and upper class R contains those rational which are not less than 1. Then 1 is a number which divides the whole rational number into two classes, or every rational number or any rational number will be either a part of L or maybe part of R. Okay? So, this will be a cut. This is known as the cut. Yes. Yes, this is this.
The last equation we are using the Q. So, X belongs to Q and X also X belongs to Q. And we are taking again the P and Q is the property. Is this two Q are same or there is?
No, Q is the same. Q is the collection of the rational number. Q is the collection of the rational number. So, from this Q we are picking up those rational number.
Here Q indicates the collection of rational
Rational number. Here also Q collects the rational number.
In the right side Q indicates?
Which right side? This one. Oh, this property. Yes, yes. I am. Yeah. So, let it be this P and Q. So, should I write this Q dash? Q1. This is Q rational. I am taking a rational. Let it be denoted by something
Sir, here I think sir here in the left,
q rational. Rational. Is it okay?
now it is
Q rational, set of rational. This property is something. Yeah. These two are not. Yeah, this is the property. Yes. Okay. Similarly, when you go for the square root of 2, okay, square root of 2, when you say it also divides the rational point into 2 parts, 2 classes, those rational number whose square is less than 2, those rational number whose square is greater than 2. So, entire rational number you can divide into two classes. One is the lower class where it the whole rational number. Similarly, second example is, suppose L I set of those Q a rational point x belongs to rational such that square of this is less than 2, okay, and R is the set of those rational such that square of this is greater than 2. So, this is the lower class, this is the upper class, and 2 is the number which is square root of 2 dividing the number, but 2 square root 2 is neither belongs to L nor belongs to R. So, basically this is this cut, this will give a cut or section corresponding to root 2. There is a this was a cut corresponding to 1, but 1 was one of the class. Here root 2 is none of the class. So, there are two types of cut, one is the rational cut, another one is the irrational cuts, and combination of this gives the continuum entire real line. When a collection of all these cuts gives the entire real line, that is known as the continuum, okay, and that this way the real line, the system of the real number has been defined. Okay. So, this is the theory given by the Dedekind, introduced in terms of the cuts. Thank you very much. Thanks. Okay.